Alright people, we are back. We are ready. Let's look at single slit diffraction. So if I shine monochromatic light, meaning one color, at a very, very thin slit, I get, you might think it would just come straight through, but actually, there we go, I get a diffraction pattern. Let me make hair here. I get a diffraction pattern. Surprise, which was a big surprise to many of the scientists back in the day. So this is called, what you get is Fraunhofer diffraction. Okay? This is a very important diagram from our textbook. What I'm getting here is a bright central fringe here. We call the central max, this thing right here. And I get less bright, thinner secondary maximums here and here and here. And I want you to note that the central max, not only is it super bright, it's twice as big as the others. Twice as big. Very important diagram right here. I have some pictures since I can't show you in class with a laser, but we see here that it's definitely twice as big as all the other maximums, and then they kind of just trail away. Here it is with green light, here it is with red, here's another picture. Definitely the middle guy is wider than all the others. Now there's explanations, you can find them online, you can find them in the textbook of why this is happening. I'm not really that interested in why. I'm interested that we can do the math. So we can have dark fringes and bright fringes. There's two formulas here for the dark fringes. W is the slit width, L here is the distance to the screen. I guess X is the distance from the center. Distance from center. And then the same down here. Oddly enough, in double slits, it was the darks that had the plus a half, and now it's the brights that have the plus a half. N is 1, 2, 3. So if I go back up here to this very important diagram, when I'm talking darks, I'm talking this is 1, and this is 2, and this is 3, or also 1, 2, 3. Now when I'm talking brights, we don't talk about the central. It's not given a number. This is number 1, this is number 2, and this is number 3. And the distance from the middle to the first dark is delta y. And that's a formula here if we go down. I give you a straight up formula for delta y here. Delta y is lambda L over W, and we can use that in our problem solving. So let's try a question here, single slit question. Light, so lambda is 5.4 times 10 to the minus 7 meters. Trust me, that's the way this works out. Slit width is 11 micrometers, which is 11 times 10 to the minus 6 meters. I get L is 80 centimeters, which is 0.8 meters. It's single, which is something that I like to put in there. Calculate the distance of the first dark fringe from the central maximum on the screen. So I'm going to go up. So I'm looking for middle to the first dark, and that distance is delta y. Middle to the first dark, delta y. So I'm looking in this question for delta y. Just slide up here. Whoa, whoa, whoa. lambda L over W. Delta Y equals lambda L over W, which is 5.4 times 10 to the minus 7 times 0.8 all over 11 times 10 to the minus 6. And if I plug that all in, I get 3.9 times 10 to the minus 2 meters. Which is 3.9 centimeters. So from the middle to the first dark, this is all bright stuff here, and this is bright. So from here, from the middle to the first dark is going to be 3.9 centimeters. Let's try another one here. So I see lambda is 670 nanometers, which is 6.7 times 10 to the minus 7 meters. I see slit width is 12 micrometers, which is 12 times 10 to the minus 6 meters. L is 30 centimeters, which is 0.3 meters. It's single, so I know which set of formulas to use. Calculate the angular width and the absolute width in centimeters of the central maximum. So basically, when I look at that central peak here, and I look at it, this might not actually be a good diagram. If this is that central dark spot or bright spot, and then I've got these ones, it's asking me, when I look at this, if that's the middle, it's asking me how wide is this in centimeters and how wide is it in degrees. Yes, I want to know this here in degrees and in centimeters. So well, centimeters, the central maximum is 2 delta y. Yes, so that's 2. Lambda L over W, 2 lambda L over W. And so I just start plugging in 2 times 6.7 times 10 to the minus 7 times 0.3 all over 12 times 10 to the minus 6, and I get 0.0335 meters, which is about 3.4 centimeters. So there it is. There's that full distance in centimeters. Now I need it in degrees. So I'll use one of the formulas up above. Sine theta is equal to lambda over W. I plug all this into my calculator, I'm going to get an angle of 3.2 degrees. Now that is only this central bright spot. That's this. This is 3.2. So therefore, the whole thing would be 6.4 degrees. So there's the central max question. the distance between the first and second minima. Well, again, if I go up to this very important diagram, distance between the first and second minima is still delta y, yes? So I should be able to just use the delta y formula, lambda L over W. Delta y is lambda L over W. I plug everything in there and I'm going to get 1.7 centimeters, and you can try that for yourself. The last question asks for the distance between the second and third maxima. I'm going to go back up because this is such an important diagram. Second and third maxima, so from here to here, yes? From here to here, and it's delta y again. All of this is the same, delta y. Plug all that in, and I get the same number. I'll tell you this for a second. Minima, determine the distance between the second and third maximum. Compare this answer to your answer in B's. Does this answer make sense? Well, yes, it should make sense because these distances from one to the other, whether it's a bright or a dark, here it's a dark, here it's a bright, it's going to be the same both ways. And this ends our look at single slit diffraction.